Hello everyone, my name is Haru and I'm a software developer on the AI Racing Tech team in the Indy Autonomous Challenge. And today, just for our software developers on the perception side especially, I will be talking about how we build our initial pipeline for perception stack in the Indy Autonomous Challenge 2022 to 2023. So the thing we'll cover today, three main points basically. Number one is we'll talk about how the problem of this perception come around, where we will be addressing some of the race rules and where that will take us. And second is we'll talk about how we use the Hardware Universe repository to build our initial perception pipeline. And then we'll go specifically through the ART repositories to find out where those packages are and how do we connect the dots to finally launch the perception stack on the car. So let's start by formulating this big perception problem really. If you're someone who is new to autonomous vehicles and addressing this perception problem for the first time, this definitely feels very challenging. And trust me, that's how exactly we feel 1 year, 2 years ago when we first started off our project on the IAC. And so the IAC has a set of race rules that will regulate how we will make our perception work. And there's also a bunch of vehicle specifications that we need to consider and a bunch of other inherent requirements with these spectacular machines running at extremely high speeds. We're going to talk about that. So a one-word, I guess a one-sentence summary of the Indian Autonomous Challenge really is that it's a two-car, high-speed, head-to-head passing competition on a oval speedway. So this just one complete sentence really says a lot about how the competition is. And the statement already gives away most of the complications as well as simplifications for this perception problem compared to, say, a commercial AV on public roads. So to summarize on the sheet here, number one, it's a two-car competition. So at any point, there will only be at most one opponent vehicle on the track that we need to detect. Second, it's on an oval speedway, which we can call it a controlled environment. You do not need to detect things like weaving bicyclists or traffic lights, things like that. But also it's an oval, so the banking angle could be tricky to deal with later on, especially when we talk about ground filterings. And number three, it's a head-to-head race. So if the competition is downright, the opponent is pretty much almost always, say, within plus or minus 100 meters of the ego vehicle. So we will always have something to detect, and the opponent will always be somewhat close to us. Then it's also a passing competition. This means as the passing is happening, the feature of the rival vehicle on our cameras, radars, and lidars will change drastically before, during, and after that overtaking. So in addition, the tracking algorithm also needs to cope with these sudden changes in accelerations during the overtake execution, which basically demands us to have a good tracking algorithm on top of detections. And finally, it's a high-speed competition. So the top teams right now are running at, let's say, 130, 170 miles per hour. And the perception system should be designed for similar operating ranges. And these problems could immediately pop up in your head, say camera motion blurs, or LiDAR motion distortions, or just simply the short reaction times due to the speed, and also the demand for a relatively long detection horizon requirements. Which is typically, say, 50 to 100 meters. So there's also other considerations that statement did not cover. Number one, there is a race control. So they will do their best to red flag the race should maybe, say, one car breaks down. So there's certain extreme cases that we don't really need to consider because there's going to be human interventions. Say we don't need to worry about a car charging towards a stationary target vehicle at 150 miles per hour speed differential. And secondly, it's a structured race with round speed targets, and this simplifies things because it's almost guaranteed that we will not always not have too much of a big speed differential between us and the target car. So each round, the overtaker usually would only be, say, 20 to 30 miles per hour faster than the defending vehicle. So this simplifies the problem a lot and makes it a more manageable overtaking problem on the vehicle dynamics side, and also a perception problem because it's not like the other car is just gonna fly across our screen from left to right in 1 second, say. And I'm also still going to talk a little bit about what we have on the vehicles, although some of you is probably already pretty familiar with this. There's 6 cameras mounted on top of the car, and they're in very different configurations. There's 2 cameras facing forward that is more zoomed in, and then you have 4 other cameras that are equipped with a fish lens, and then are put on the pointing at the left, the right, the rear left, and rear right of the car. And they're global shutter cameras, so they don't suffer from heavy motion blur issues. Although some of the perception teams might find the camera itself being really tricky to deal with, but that's mostly a manufacturer's problem. So second is we have 3 Lumina Hydra LiDARs. That is actually their last gen model, not the latest. And these LiDARs are pretty much covering the entire 360s of the car. Each of them have 120 degrees field of view, and their configurations allow a variable frequency from 10 to 30 hertz at the cost, of course, that if you're at 30 hertz, you're going to get less horizontal scan lines from the LiDARs, and if you're at 10 hertz, you get a richer cloud at every scan, but also your frequency is drastically reduced, and we in general find that to be a very bad thing for tracking problems especially. And we also have 3 active radars, front, left, and right. These are common types on passenger AVs. And finally, we have 2 Novotel GPS, which gives you centimeter accuracy when the GPS is actually good. And also, of course, if later on we are at track with not so good GPS, we would turn on our localization solutions and still be able to dead reckon to a similar degree of accuracy for a limited amount of time. And so this accurate position is important later when we talk about off-map filtering, which means we want to filter things that is not important to us, aka things that are off the racetrack. So a couple special note on the vehicle specifications. Number one, there's just this huge blind spot behind the vehicle, which we can visualize here on the screen. Here on the immediately behind the vehicle, you can see this black area here, which is not covered by any LiDARs and also not by any of the cameras. And this could be a detection problem if in the future, for any reason, the IAC decides that the car in the front has responsibility to actually detect a car that's immediately behind it. But so far, that hasn't been a concern, and it is purely okay right now for us to even lose detection in that range with the opponent vehicle. And second thing is the sensor mounting points are subject to fluxings and misalignment. Basically, where the IAC is mounting the sensors, that is just a thin metal plate with some even anti-aberration rubbers on it. And every time the crew takes a look at the cockpit for maintenance, that plate is actually removed. So this could cause a big calibration problem, and it seems that from the experience of other teams doing it, they quite frequently recalibrate the sensor positions between runs. And that's just one thing to take note of for people doing 2D or 3D fusion problems. And here are a couple other inherent requirements that derive from just the whole fact that we're dealing with a vehicle running at 170 miles an hour. So number one is there's a strong real-time requirement. Everything needs to be computed in a timely fashion. We aim for at least a 30 hertz goal, output goal on the perception stack, and this only leaves 30 milliseconds of processing time for each camera or LiDAR frame that's coming in, which are also approximately at 30 hertz. And some algorithms would make it, especially those in C++. Some, especially those in Python, doing for loops may not. So that's one big thing to consider. And second is we have software reliability constraints. This means the software needs to be robust against a couple situations, like what if you get a blank frame on your camera or LiDAR? What if you somehow get NaN values in the middle of the perceptions, which is actually could be a pretty frequent problem. If say you are running a Kalman filter for tracking a moving vehicle, it's pretty frequent that a Kalman filter that's not so properly written would give you NaN values after a certain time, and you have to be reliable against that. So if errors do happen, the software should have exception handlings, not just rage quit on us during the middle of a run. This includes the use of try-catch statements in softwares and also using ROS lifecycle for managing node errors. In general, there should be just good software practices along the way when we're developing these perception modules. Couple rules of thumb. Number one, consider trading data load which is things like LiDAR density and image resolution with the detection accuracy. We don't really need a 2K image to do YOLO detection, for example, which gets shrinked to 640 by 640 anyway. And on the LiDAR, things get a little bit trickier because the data is much more sparse. And also to get a 30 hertz frequency output on the LiDAR, we have to pretty much drop a lot of those points, but still there's ways we can do to increase the density by setting the distribution of scan lines on the horizontal areas. And so that's trading data load with detection accuracies or even frequencies. And second thing is you might always want to do a development in Python, but also later on convert things to C++. That usually makes the code run faster. And even if you would stay in Python, it's a good idea to use vectorized operations like NumPys and QPys and parallel processing libraries like multiprocessing. This is always a better idea than using Python for loops. So those are the requirements that the race have given us. We're in this two-car head-to-head competition. We have to detect this other car. We can ignore a lot of the complications of environments that is common in urban autonomous driving. And these are high-speed vehicles, so there's a lot of high-speed requirements and safety requirements and real-time requirements that we need to deal with in the perception space. So this brings us to Alder Universe. This is the main open source solution that we've been using on the perception side. And I'll just talk a little bit about what's Alder actually, and then introducing slightly what are the Alder Universe modules that exist. So who is Alder? It's actually a nonprofit organization that's on a global level. And it supports many open source autonomous driving projects, especially its own project, which is the Alder Universe project currently. And who's in the Alder? Well, it's a bunch of private companies, education institutes, and government bodies. Some names that you might be really familiar. From the education side, TUM, for example, is right now a big partner in Alder. And so how Alder really works is that the member companies and these institutes contribute software engineers to work on the Alder source code. And later on, how they profit is once the whole Alder project is complete in its current ODD, they profit from selling these autonomous driving services that are targeted during a specific Alder ODD development. And some of these recent examples include, for example, autonomous valet parking. That was the first Alder ODD. and cargo delivery, and then finally autonomous bus, which is the goal for Autoware during 2022 to 2023. And the member companies of Autoware comes really from different sectors related to autonomous driving. It's not just companies that's actually doing autonomous driving services. You have more traditional AV companies, of course, Tier 4 Leo Drive. They are actually selling these AV solutions. But also you would have people like map and simulation providers, TomTom, which is a very big map provider, Morai, which some of you have joined some Autoware meetings, you might be hearing them talking about using their simulations, integrating it with Autoware. And there's many computation platform providers in Autoware. ARM, for example, is part of Autoware, and DSpace, which provides the computer we use on the IAC car, and AD-Link, which previously provides the computer we use on the IAC car, and AMD is also part of the Autoware support. And the other big fashion is the sensor OEMs, Hexagon, which produces those Novatel units, RoboSense, which is a big LiDAR company, Velodyne, which is another one. And there's also just a bunch more companies in Autoware that's basically providing their softwares and contributing engineers and work on the Autoware project. And obviously, most of these companies are relatively like small compared to the top tier autonomous vehicle companies like I don't know, Tesla or Waymo, Cruise, the other guys. And this is why there is Autoware. It's because the individual companies are not strong enough to develop the entire stack, so they kind of partner with each other and then come out with this open source platform. So why is it called Autoware Universe? So Universe is a terminology against core. So this is the structure that Autoware decides to take on in early 2022, where they will merge a bunch of old Autoware projects and then put it out as a Autoware Universe plus Autoware Core. So Universe contains all the experimental AV packages that is currently being developed with the Autoware ODD. And once these things are stable, they get moved into the Autoware Core, which Autoware has actually just recently announced that they will be moving some of the autonomous bus ODD package into the Autoware Core repository. So if you go to the Autoware Universe repository, which we will be doing in just a second, you're going to be seeing things being broadly separated into these folders, which is not uncommon in autonomous vehicles. Controls contains all the vehicle controllers. Plannings contains the behavior and motion plannings. Sensing and perception are the parts that we will be using the most on the perception side. So sensing is more like low-level perception, so sensor pre-processing. And perception is actual high-level detection and tracking algorithms like YOLO, LiDAR sensor points, multi-object tracking with Kalman filters, things like that. Localizations contains a bunch of localization solutions like odometries, NDT localizers with LiDARs, things like that. Simulators bridge with simulations, and vehicle folder contains packages that bridges with real-world vehicles. So next up, we'll be diving deep into the ART repository. And basically, I'm going to give a walkthrough of how the perception pipeline was initially built. And this just includes a walkthrough process of how do you basically dig around in the Autoware Universe repository and find information that's related to your applications. So with that, let's head over to the Autoware Universe repository. And just a quick note that the upstream Autoware Universe repository is actually getting updated very frequently. So if you want to access the version that we use in Everything Tech specifically, you would want to head over to our private fork, which is a couple months behind the master branch, but also we usually don't touch the our fork before the race, just because we want a stable version throughout. So on the Algorithm universe, you just see the folders that I just talked about, things being separated into different places. So let's say that you're someone who's looking at the Algorithm universe repository for the first time, and you have a very specific perception problem in mind, like the thing we've just talked about, all the requirements that's been given to you from the IIC. Then you would want to start to work with a very bare minimum perception stack. Like, where would you start? Well, the first thing to consider is since it's a bare minimum stack, you might not have a lot of time to do it. Anything that requires, for example, deep learning is probably a little bit beyond your timeline. So you would basically start with more traditional ways of doing perceptions. And this is where something that might be not very apparent, but if you have previous experiences with AVs, you might know that clustering methods, for example, with LiDARs, is a very effective way of just acquiring clusters of objects in the environment. So that's when I started this project, I first started looking into. So I know there's a package called Euclidean clustering, and obviously I will just access it probably somewhere in the perception folder, and there it is, the Euclidean cluster. And every Algorithm universe repository has a README file. This is your best friend. It basically tells you what are the input and output message formats of this node, what it does, and also what parameters does this node have. So just by looking at the inputs and outputs, you can see that the Euclidean clustering takes, well, a point cloud, and it also outputs something called the tier 4 perception messages, which is not apparent, but, well, in the description it tells you it's just the clustered point cloud. There's also a debug message, which is just for visualization purposes. But we'll just stick with the tier 4 perception message for now, because that is our main output. So with that, now you know you have a node that is called Euclidean cluster that takes a bunch of point clouds and then basically spits out these clusters, which are still points. They're not bounding boxes or anything fancier yet. So the next step is really just going from here, going upstream and downstream, what are the required nodes. And going upstream, it's more apparent. I need this input pre-processed point cloud, and although the entire pre-processing stage is complicated enough that it's worth a separate discussion. But I know that it's more manageable. Like, I know where things roughly would be, right? I would have 3 point clouds, and I somehow need to concatenate them, and then maybe even filter out some of the non-relative points, and then provide that as an input to the Euclidean clustering. So I know about that part. That's relatively easy. But looking downstream, I'm not quite sure how from this cluster of points can I get a bounding box out of it. So this is where you might want to start to look, dig around a little bit and see how Autoware has been doing in its example launch files. So let's head over to the launch, and here there's examples provided to basically tell you how to launch different part of Autoware. Here in the perception launch, let's see what it does have. Ground segmentation doesn't matter. All these other things doesn't matter. Optic recognition sounds plausible, and at this stage we're just dealing with the detections, nothing else. And here you are, there's detections coming from different kind of methods, camera LiDAR fusion, LiDAR-based detections, which sounds like what we need. LiDAR radar, well, we're not that fancy yet to use radar. So let's take a look at the LiDAR-based ones. And this is a XML launch file, which, to those of you that's familiar with Python launch files, may not be easy to read, but you can basically get an idea of what it's trying to launch. So from the inputs, there's some clustering nodes that you can choose. And here's a node to basically remove the, well, this node is actually a little bit tricky. We're going to talk about it later. But here down from the clustering, you'll see a node called shape estimation. And this is actually, well, according to this is actually going to be taking the output of the Euclidean clustering and doing something called a shape estimation. I wonder what that means. And after shape estimation, it seems that it goes through a object feature remover, which also I'm not so sure what that means. But then it seems that it just comes to a bunch of tracking components, which we can deal with a little bit later. So let's head back to see what does it mean to do shape estimation. Let's go back to the perception folder and identify the shape estimation. And let's just read that through a little bit. So it basically says that if you give it a point cloud cluster, which is exactly the output of the Euclidean clustering, it can actually compute a object shape using a variety of different methods like bounding box, cylinder, and convex hull. And it looks like it's using different fitting algorithms for different types of vehicles or even pedestrians, which was the original intended detection by AutoWord, although not relevant in our use case. So here it says that basically, if you read it through, it says when using the bounding box, a bounding box will be used for vehicles. Cylinder is used for cyclists and pedestrians. And convex hull is used for just other kinds of big unrecognized objects. And let's look at the input and outputs. It actually exactly takes the message type that was the output of Euclidean clustering, no surprise. And it outputs a detected object, which will give you that bounding box, which is nice. And the exact algorithm of the bounding box, if you're interested, you can check out the L-shaped fitting paper that they linked here, which basically talks about you can extract a L shape from the later scans of a car usually, because cars are usually box shaped, and then shining a laser LiDAR on it usually gives you just two sides of that box, and that's an L shape fitting that these people used to work on. Looks like now we have actually a detected object output. That is nice. That sounds like a very final stage of the detections. And if we have something, if we have the detections, that's probably not going to be enough for us to track the vehicles. And this is where the tracker comes into place. So after detection, there's usually a stage of tracking. So let's see which of these AutoWord node does tracking. And the answer is pretty obvious. If you just search tracker, and there is a code, multi-object tracker. And if you read through the algorithms and everything, you can see how it does a data association algorithms. And then it has EKF motion model for different kind of vehicles, people, and bikes. And it just takes that detected object that we just talked about, and it actually outputs a tracked object, which is supposedly much more reliable than the detected object. And also by updating motion models, it gives you the velocity of the thing that you're tracking, which is useful in our case because we want to get the target vehicle's velocity to implement, for example, following behaviors. So, so we've just looked through 3 or 4 nodes, and we've now already have a very bare minimum AutoWord perception tracking stack. So we will start with Euclidean clustering, and then we output the clusterings to the shape estimation node, which gives us a bounding box. And then finally, we feed that into our tracker, which then basically produces the tracked object that the planning stack can use. So that completes basically the first iteration of the ART perception stack. Very easy. So then as we develop the entire stack, now we also need to go upstream. So going from the Euclidean cluster that we just talked about, going upstream, I still need to get this concatenated input point cloud. And that means I need to somehow get it from the 3 LiDAR sensors I have, which is outputting point clouds at different frequencies. That's trouble number 1. And trouble number 2 is they are pretty high density sensors that's producing a lot of points, so I might want to downsample that, and that might be a lot of computation powers because I also have real-time requirements to consider. And also I may want to do some filters because if you visualize the raw point cloud on the car, some of it is actually hitting the car body itself. So I need some filter to also remove these points to prevent them from being classified as something. So with that, let's start exploring the outer universe sensing folder. And among all these packages, most of them doesn't really make much sense until you go to the point cloud preprocessor, which sounds exactly what we want to do. And there's all these 10 different kind of filters that you can apply. And here's also where you may require some ROS knowledges because these nodes actually use the ROS2 component to launch. And something that's going to be apparent when you look at examples here in the preprocessor example launch files. They launch these nodes into composable nodes, meaning they run things on the same thread, one after the other. And there's also some accelerations of memory copyings or things like that. And I'm not so sure that you can get out of this way of launching nodes in a composable node container. So let's see what different nodes they provide here that we might be able to use. Concatenate, well, that sounds very useful. We have 3 point clouds. We want to concatenate them together. And I'm just taking a brief read out of the algorithms. They talk about, how maybe even points from different times are aligned or sort of aligned with each other. And then also there's cases where the points may be dropped. And this is final output of concatenate topic, which is just a rough bundle of the 3 latest points that's coming in. Okay, so this first node here will help us stitch together the point clouds, which will probably be a very late stage, say immediately before the Euclidean clustering, when we are ready with all the point clouds. The second thing is called the crop box filter, remove points within a given box. Also sounds very useful. It can actually help us remove the points that's shining on the rear wings and wheels of our car. So if we define the box that's of the right shape, we can filter them out. And the other thing that the document hasn't mentioned is actually this node can also be used to remove points that's outside of a box. So potentially this means we can define a very big box of say 100 meter by 100 meter, and then just remove everything outside of that. Because say just naively everything outside of that is something that I don't really care about in the perception stack. So that's another useful node. Distortion corrector, something that we don't use, but something that is good for future work. It compensates the point cloud distortions with the ego vehicle movements. This is just because the lasers from the LiDARs take time to shine, and different skylines, there's time differentials between when they're taken. So it's best if we use the velocity of the car to correct for that. And this distortion is also actually very apparent on their high speeds. And especially if you're using deep learning based detections, it's a good idea to de-distort the point cloud before you pass anything through that. Although clustering is mostly fine, because we don't really depend on the correct the correct geometry of the object to be able to cluster it. As long as it's a blob of points, including clustering will just detect it. But deep learning, well, it probably wants the car to be in the right shape to be able to really detect it. The next node, downsampling filter, sounds also very useful. If you try to run the ART perception stack with just a raw point cloud, you're going to get a very rough hertz out of the Euclidean clusterings, which is simply overloaded by the excessive amounts of points that these luminar lidars are putting. So the downsample filter basically just downsamples the points using a variety of methods. And in the end, you just get a more sparse point cloud, which is good or bad. And this step requires the most amount of tunings to get to the right downsample size. So outlier filter, which is something we don't care. Other problems, raindrops, small insects. These are more reliable passenger vehicles. Pass-through filter, again, something we still don't really care, but it's useful. It kind of works like the crop box filter, except it just does it on a more direct way on the X, Y, and Z, which I guess can potentially save a little bit more time on the pre-processings. The point cloud accumulator, something that we also don't usually care much, and it's in fact something that we can't use, just because we're moving at a really high velocity. So if you're accumulating 2 point clouds together without considering the transforms, it's a bad idea. And also the other car might have moved for a very long distance during 2 point clouds. So usually we don't really do accumulations. This is more for passenger AVs. Vector map filter and vector map inside area filter, all of these relies on having an accurate map to filter things that's not on the map. And we do similar things because we want to filter out things that's outside of the racetrack. And we have our own way of doing it by using the polygon filters. The polygon filter, it used to be a thing in the Auto repository, which is the last generation of Auto, where we can simply provide the node with a polygon dynamically, and then it will just filter out points that's outside the polygon. But it's becoming a little bit tricky in this iteration of Auto because the polygon remover here does not directly take a polygon ROS2 message. It only takes a fixed polygon, because presumably people only want you to use it to remove, say, points outside the geometry of the eco vehicle, which may be a polygon. But we are using it to remove a wider area of points because we are drawing the track inner and outer boundaries as polygons, which can be visualized here on these 2 lines, and then filter out everything that's outside of these polygons. So other than writing our own polygon transformer, which transforms this polygon into the correct frame of the LiDAR and then publish it, we also modify the Auto source code in the ART fork of Auto to take a dynamic polygon and then filter points that's outside of this polygon dynamically. So that node does similar things to the vector map filter, which filters points that's outside of the map. So these are all the pre-processing packages that Auto provide. And of course, there's a lot of tuning efforts in here to figure out what node works and doesn't work, and how it works, and what parameter make it work. But in the end, looking at this very intimidating ART stack RQT graph, you'll be able to find some of these nodes in this graph. And although this whole graph looks very big, we can really just start from here, where there's all these input point clouds coming in, the luminar left, right, and front, and all of them goes through these three pre-processing boxes, which does the exact same thing. So we'll just take a look at one of them, say the top one, and I'm not write points. You can see when it comes in, it first goes to the scan ground filter, which is something we actually haven't talked about yet, but it's a ground remover. And the only thing it does is that it removes points that's shining on the ground. And once that is removed, it goes through the downsampler, which we just talked about. It helps to boost the frequency of the detection pipeline so that the later algorithms are not overloaded with points. And the output of the three downsamplings are concatenated together. And that single big point cloud, which is called points raw concatenated, is then going through further processing, such as the crop box filter, which filters everything that is, say, 100 to 200 meters away from the Eagle vehicle. And then it goes through the Eagle crop box filter, which just removes the points that shines on the Eagle car itself. And it goes to the polygon removers, which is supplied with a polygon, which might be a little bit hard to read, but it's supplied with polygon from the boundary transformers, and gets removed once for the inside and twice for the points on the outside. And in the end, you just end up with points that is on the track, that is not the ground, that is not the Eagle vehicle. And what that point might be? Well, there obviously must be the opponent vehicle. So then those points are passed through to the Euclidean clusterings, which outputs the message called a cluster with features, which are just basically a bunch of points. And from this point on, this is where things might get a little bit confusing. We can ignore the detection by tracker bit first. But the cluster with feature goes through the shape estimation, which conducts a L-shift fitting. And then in the end, it gives you bounding boxes. And this detected object feature remover here, which we just talked about, is nothing but a message type converter, which converts tier 4 messages to auto messages. Other than that, it does absolutely nothing fancy. It's just a message API compatibility thing that, because the many of the auto universe perception packages actually comes from tier 4, which is a big company in the Autoware Foundation. And they use their internal tier 4 messagings, and to get it to be compatible with Autoware, there's finally this stage which converts their message to Autoware detection messages. So we are done dealing with the pre-processing and the detections. Now I'm going to talk about a little bit more advanced tracking modules. You'll see the multi-object tracker here at the very end. But also you can see there's a couple nodes before that, mainly two that I haven't talked about. One is called the detection by tracker, and the other thing is called the tracker detection merger. So these two nodes haven't been fully investigated or debugged, but I can generally talk about what they do. So the detection by tracker node provides a feedback loop, basically. If you head over to the description page, basically, it explains here that if you want to get a stable, reliable tracking result from the multi-object tracker, you can feed the tracker output back to a early detection stage and use this detection by tracker node to basically take the tracker's output also as a input for detections. And this can be merged with newer detections that is coming in. So basically, it's merging the predictions of the tracker with the new detections coming from the sensors. And this is just a great way of enhancing the reliabilities of detections. So even if your detection is dropping for a frame or two or even more, because the tracker results is still coming in for a couple of frames, although with increased uncertainties and covariance values, it can still hold on to that for a couple frames before it completely drops out. So this is the feedback loop that you're seeing here, that the multi-object tracker is feeding this back. Oh, it's a poorly driven graph, but it's feeding back the tracked object back to the detection by tracker node. And the detection by tracker node is also taking consideration the output of the Euclidean clustering and output a message called the tracker detected object, which, I mean, just tongue twisters, but it's a detected object by the tracker. And later on, it goes through this merger node, which is also as described here, the object merger, which is a different node here, which provides a method of merging two detection methods by using data association. How it works is basically it has a different bunch of parameters that you can tune, which basically says, if two detections are in this much of overlap or they are this much alike, then we'll just treat them as the same detections. That's just the key idea of data associations. So, and after we merge the track detected object with the original Euclidean clustering detected object, then it finally outputs a merged object, which goes into the multi-object tracker. So this is everything we have so far on the first ART perception stack. And I'm walking this through just as someone who's developing this at the same time, at the first time, what you would be looking for. And the way I started is I know there's an algorithm called Euclidean clustering. So I will essentially start from here and work my way upwards and downwards. Working my way upwards, I know it's relatively easy. I just need to figure out a pre-processing stage that makes sense, that would basically remove everything that is irrelevant and only gives me points that represents the opponent vehicle. And going downwards, it may be a little bit tricky. I need to do a little bit of digging around in the other repositories and to find the right packages to use. And one good friend is all the example launch files they've already provided in the other universe. And this is how I was able to find the shape estimation node and also a bunch of nodes that come after that. Basically how they build the entire multi-object tracker and the tracker feedback loop. And going upward, these pre-processing launch file examples, you can actually find them in different other repositories like the SensorKit launch. If you go into there, go read the Point Cloud preprocessor launch. It actually already launches a lot of these examples that we just talked about. And they launch it inside of a compatible node container. And this is also, as I just said, this is the stage where it requires the most amount of tunings to make everything work, but still you would just do it one node at a time. Make sure that the prior output of the previous stage is already working before you start to go to the next one. But there's just basically months of tuning works going into these preprocessing nodes to make them work as intended. So yeah, that's all I have for this session of perception walkthrough. Feel free to let me know on Discord or emails if you have any questions. And if we have chance in the future, we can also go talk about more advanced topics like how we would do things for the next stage, leveraging 2D perception data and some of the deep learning modules that Alder also has to provide. And also what's some of the good DevOps practices in our perception pipelines. And so that's for a different time. So thank you so much.